Deep in the vast silence of space, a discovery emerged that would challenge everything we thought we knew about the origins of the universe. It didn't come from a lab, a particle accelerator, or a blackboard filled with equations. It came from a telescope, one so advanced it could peer into the dawn of time itself. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, was designed to look back over 13 billion years into a time when the first galaxies were just beginning to flicker into existence. But what it saw wasn't the chaotic, unstructured universe scientists expected. It was something far more organized and far more unsettling. Within a patch of sky filled with ancient light, the telescope detected a galaxy. Not a crude cluster of gas and dust, but a vast, mature spiral galaxy, complete with a defined core and sweeping arms. A structure that, by all accepted cosmological models, shouldn't have been there. Not that early. Not when the universe was less than 400 million years old. This wasn't just a surprising find, it was a direct challenge to the foundation of astrophysics. The early universe was thought to be unstable and wild, a sea of energy and particles still settling into the first stars. Those stars, massive and short-lived, should have burned out quickly, forming irregular galaxies in scattered pockets. But this new galaxy suggested something very different. It pointed to the possibility that cosmic evolution may have happened much faster than anyone believed, or through mechanisms we still don't understand. The implications were staggering. If such galaxies existed so soon after the Big Bang, it meant that the essential ingredients for complexity, dust, heavy elements, stable stars, had to be present far earlier than predicted. This raised new questions about stellar nucleosynthesis, the process by which stars forge elements heavier than hydrogen and helium. Either the first stars formed, lived, and died in a fraction of the time expected, or an entirely new process was at play, something not accounted for in current models. Scientists were left with unsettling possibilities. Was dark matter playing a more active and creative role in shaping the early universe? Was our interpretation of redshift, used to measure the age and distance of cosmic objects, flawed? Or could this be a hint of new physics altogether, requiring changes to our understanding of gravity, time, or even the fabric of space itself? The mystery only deepened with further observations. Webb began to detect more of these ancient, impossibly well-formed galaxies. Their light carried unusual chemical fingerprints, traces of carbon, oxygen, even iron. Elements that should not have existed in such abundance in the early universe. The first stars were supposed to be made mostly of hydrogen and helium, the basic building blocks left over from the Big Bang. But here, in the spectrographic data, were signs of a universe already rich in the ingredients for planets, life, and complexity. What James Webb had uncovered was not just a window into the past. It was a crack in the narrative of how the cosmos came to be. And through that crack, new questions began to pour in, questions that may redefine our understanding of space, time, and the very beginning of everything. These elements, carbon, oxygen, iron, are not born in the emptiness of space. They are forged in the hearts of stars and cast into the cosmos through the violent deaths of supernova. For such materials to appear in abundance within this ancient galaxy, entire generations of stars would have needed to live, burn out, and explode, all before this galaxy ever took shape. That idea strains the boundaries of possibility. It would mean that stellar life cycles happened at speeds far beyond anything accounted for in current models, or that some other, unknown process created these elements through means we have yet to discover. More puzzling still was the galaxy's form. Its structure was not random or chaotic. It was elegant, defined. Its spiral arms curled gracefully around a radiant core, not as scattered filaments of dust, but as tightly bound currents shaped by time and gravity. This level of order demands more than age, it demands balance. Galactic interactions, gravitational pulls, and the quiet shaping of countless orbits over hundreds of millions of years. And yet, here it was, appearing impossibly early in the cosmic timeline. How could such structure arise so quickly after the birth of time itself? The framework of gravity, the scaffolding that binds galaxies and forms their shape, should not have stabilized so soon. Massive black holes, believed to reside at the center of nearly all galaxies, are thought to take eons to develop. But if this galaxy's structure already revolved around one, then something about our timeline for black hole formation is deeply flawed. Then came the galaxy's behavior revealed in its light curve, the pattern of its brightness over time. Rather than a calm, consistent glow, the data revealed bursts and fluctuations. Signals that hinted at intense activity, possibly from an active galactic nucleus, or even a quasar among the most energetic phenomena in the universe, driven by supermassive black holes devouring matter at extreme rates. If such forces were active this early in cosmic history, it suggests that black holes not only formed rapidly, but reached enormous sizes in a fraction of the time previously believed. This alone would demand a complete rethinking of how and when these cosmic giants arise, and what conditions in the early universe allowed them to grow so quickly. But the implications don't stop at galaxies and black holes. They ripple outward to the formation of planets, and perhaps even life itself. If galaxies could mature this early, and with such a rich mix of chemical elements, then the ingredients for rocky worlds, silicon, iron, carbon compounds, even water could have existed billions of years earlier than we thought. And if planets could form sooner, could life have as well? The discovery left scientists staring not just at an ancient galaxy, but at a rewritten script for the universe, one where the clock may have started much faster than we imagined, Chatchit said. This discovery didn't just challenge our understanding of cosmic structure, it reshaped the timeline for life itself. Earth is a relatively young planet, around 4.5 billion years old. But if galaxies like this one existed when the universe was still in its infancy, then habitable conditions, worlds with water, carbon, and energy may have been possible billions of years before our own planet even formed. The window for life in the universe may not just be wide, it might be far older than we ever imagined. Thanks to the precision of the James Webb Space Telescope, scientists were able to examine this galaxy with a level of detail once thought impossible. Its resolution allowed astronomers to map individual star-forming regions and track gas flows spiraling through its arms. These weren't just pretty images. They were revelations, proof that the early universe was not a chaotic void, but a place of remarkable order and complexity. A place that shouldn't have existed according to the models, but did. It was as if Webb had tuned into an alternate version of cosmic history. One that didn't follow the expected script of slow, gradual development, but instead revealed a universe that matured quickly, acted strangely, and evolved on a schedule no one predicted. And perhaps most astonishing of all, this galaxy wasn't alone. As Webb continued to scan the deep sky, more galaxies began to emerge. Galaxies that were just as large, just as luminous, and just as baffling. What was once dismissed as a fluke now appeared to be part of a much bigger picture, an entire chapter of cosmic history that had gone unread until now. This wasn't a tweak to existing theory. This was a paradigm shift. One so significant it threatened to undo decades of astrophysical assumptions. In that single observation, the Webb telescope had done something extraordinary. It didn't just reveal a galaxy, it exposed a flaw in how we understand the universe itself. According to current physics, a galaxy of this scale should require billions of years to assemble. But this one had done it in a fraction of the time. It had formed, matured, and sent its light across the cosmos when the universe was still in its early dawn. The ripple effect was immediate. Every model of galaxy formation, every calculation about dark matter and gravitational influence, every tidy timeline of cosmic evolution, now all under question. As scientists scrambled to make sense of the data, some turned to ideas once considered fringe. Could this galaxy be evidence of a previous universe, one that collapsed and gave rise to our own in a cosmic cycle? Was it a leftover remnant from a reality that predated the Big Bang? Or was it something even more radical, a hint of higher dimensions, or interactions between universes that left imprints on our own spacetime? These theories were no longer the stuff of science fiction. They became essential tools in confronting an observation that refused to fit anywhere else. This ancient galaxy wasn't just another data point. It was a warning sign, a cosmic flare reminding us that the universe may not be as linear, as logical, or as limited as we once believed. It called into question the idea that time flows in a single direction, or that matter behaves the same in all eras. It opened the door to a vision of reality where galaxies form under rules we haven't yet discovered, where creation itself may be older, deeper, and far more mysterious than our equations suggest. The James Webb Space Telescope had done more than expand our view of the universe. It had pulled back the curtain, revealing how little we truly understand about it. And as more light from that impossible galaxy continues to reach its senses, one thing becomes clear. The deeper we look into the cosmos, the more the universe begins to look back, and the more it seems to ask questions we're only just beginning to understand. Researchers raced to interpret what they were seeing. They pored over the data, recalibrated simulation models, compared observations across multiple wavelengths, and searched for any framework that could contain the weight of this discovery. Yet, despite all efforts, the galaxy remained a riddle etched not in stone, but in starlight. A silent reminder that even in an era of unprecedented technological achievement, the universe still harbors mysteries so vast they escape the grasp of human imagination. This singular discovery, light from a galaxy that traveled across the entire age of the universe to reach us, marked the beginning of something greater than just a scientific revelation. It marked a new era, not one of certainty, but one of humility. The moment the image was captured, the curtain lifted, not to reveal a clearer cosmos, but to reflect something deeper. It showed us that what we know may be dwarfed by what we don't. The James Webb Space Telescope, built to illuminate the past, had instead cast a long shadow over our understanding of reality itself. Because in deep space, the truly impossible does not mean false. It means undiscovered. With that image, a new chapter in observational astronomy began, one that broke away from the carefully written script followed for decades. As more data arrived, it became clear this was not an isolated event. This wasn't just an exception. It was the first crack in a vast, unseen wall built from centuries of assumptions. The more researchers looked, the stranger things became. What made this discovery even more unsettling was its elegance. The galaxy's structure wasn't just surprising, it was eerily perfect. Its internal spin, its rotational balance, the way its mass was distributed, all suggested a mature, evolved system. But that maturity was far too advanced for its age. By current models, such stability and complexity require billions of years' time for galaxies to collide, merge, evolve, and settle. But this galaxy had done all that in just a few 100 million years after the Big Bang. This stability didn't just raise questions, it broke causality. It suggested that the laws of galactic formation might be embedded more deeply in the structure of space-time than previously thought. As scientists examined the galaxy's motion and the way its light bent space around it, even more anomalies emerged. The gravitational pull of the galaxy was disproportionate to its visible mass. Typically, this kind of discrepancy is attributed to dark matter, the mysterious substance thought to form halos around galaxies. But this time, something didn't add up. The gravity was concentrated, focused, clean. It wasn't smeared across a vast halo as expected. It was precise, symmetrical, and unusually ordered. This raised a new set of questions. Was this a different kind of dark matter? Or was it something else entirely, an unknown state of matter? Or even a modification to gravity itself that only reveals its effects under certain cosmic conditions? These weren't fringe ideas anymore. They were becoming the only reasonable explanations in the face of a galaxy that refused to behave as expected. Adding to the mystery was the galaxy's solitude. In the early universe, galaxies usually formed in clusters or along dense cosmic filaments, shaped by mutual gravitational forces and shared cosmic environments. But this one stood alone. No nearby galactic neighbors, no signs of past collisions, no tidal tails or warped arms. It floated in an unusually clean pocket of space, untouched by the usual chaos of early cosmic evolution. And this isolation defied logic. How could such a massive, well-formed galaxy arise without the gravitational support or disruption of a larger cosmic neighborhood? There were no easy answers, only more questions. This lone galaxy, born in the infancy of time, stable in its structure, rich in its elements, isolated in its position, and strange in its gravity, was not just a curiosity. It was a revelation, a cosmic whisper from the edge of understanding, daring us to look again, not just at the stars, but at the assumptions we've held since we first looked up. And for the first time in a long time, astronomy had no script. Only wonder, Shachby said. The idea that such an intricate and well-ordered galaxy could emerge in a seemingly untouched pocket of the early universe sent shockwaves through the cosmological community. It suggested that the large-scale structure of the cosmos might be far more flexible, perhaps even chaotic than previously thought. The geometry of the galaxy was no less startling. This wasn't just any spiral galaxy. It bore the hallmarks of a barred spiral, a form typically believed to arise only after billions of years of gravitational refinement. A prominent bar stretched across its center, flanked by clearly defined arms rich with star formation. In conventional models, barred spirals evolve from normal spirals through gradual, long-term processes, gravitational resonances, internal migration of stars, and the slow accumulation of galactic material. To see such complex morphology in what should be a primitive galaxy raised a provocative question. Had the universe developed a fast-track mechanism for galaxy evolution, or were scientists only now beginning to uncover a different set of physical laws governing early cosmic architecture? The surprises didn't stop there. The light spectrum of the galaxy also defied expectations. Objects at such high redshift typically emit a dim, reddish glow due to the expansion of the universe stretching their light. But this galaxy displayed something else entirely. Ultraviolet gradients, flickering patterns of near-infrared light. Its colors seemed to shift over time in ways that couldn't be fully explained by redshift or Doppler motion. Some researchers, stretching the boundaries of conventional thinking, proposed a wild hypothesis that these oscillations might be the result of quantum interference patterns on a cosmic scale, waves of energy and information interfering in space itself. An idea straight from the edge of science fiction, yet grounded in data so clear it couldn't be ignored. Others proposed that the object might not be one galaxy at all, but a layered projection of multiple galaxies overlapping due to gravitational lensing, or some unknown distortion in spacetime. In response to this encounter, theorists turned back to the archives. They began sifting through older data from earlier missions, Hubble, Spitzer, and others, wondering if similar galaxies had been quietly observed, only to be discarded as statistical noise. Faint anomalies, overlooked signals, subtle patterns dismissed by automated algorithms. Suddenly, they were seen in a new light. Maybe, scientists thought, these impossible galaxies had always been there. Maybe our own biases, our need to see what we expected, had blinded us to them. the implications were sobering. The universe may have been showing us the impossible all along, and we weren't ready to see it. Perhaps the most haunting question that emerged from this discovery revolved around time itself. Some researchers began to question whether time might not be constant across the universe. Could different regions of space experience time at different rates, influenced by the distribution of energy and mass? This led to the theory of cosmic time bubbles, zones where time could expand or contract, depending on the curvature of local spacetime. In this framework, the galaxy in question may not have formed in a rush. It may have evolved at a normal pace, but in a region where time moved more slowly. From our point of view, it would appear to have evolved impossibly fast, an illusion caused by relativistic differences in the flow of time. Speculative, yes, but the idea offered a rare link between the unpredictable world of quantum physics, the structure of general relativity, and the emerging frontier of cosmology. Another theory went even further into the realm of metaphysics. The holographic principle, long discussed in theoretical physics, posits that the universe we experience in 3 dimensions is a projection of information encoded on a distant 2-dimensional boundary. If true, it would mean that the galaxy Webb observed was not a material object in the traditional sense, but a kind of rendered output, a pattern projected from a deeper cosmic reality. In this light, the galaxy may have been less a place than a message, an imprint of the fundamental structure of the universe itself. And if that were true, then perhaps what Webb had discovered was not a galaxy, but a glitch, a tear in the veil. A moment where the cosmic simulation revealed something it wasn't supposed to. This pushed astrophysicists toward even stranger possibilities. Could the strange object be a remnant of the inflationary epoch, those first explosive moments after the Big Bang, when the universe expanded faster than the speed of light? Inflation theory predicts that quantum fluctuations from that era could have been stretched across galaxies, seeding the structures we see today. But what if some of those fluctuations were larger, more organized, or preserved in unexpected ways? And what if, just maybe, this galaxy wasn't formed during the universe's early days at all, but instead belonged to a realm, a process, or a principle that our science has yet to grasp? The encounter had opened not just a new chapter in astronomy, but a new vocabulary of possibility. The only certainty left was that nothing, absolutely nothing, could be taken for granted anymore. Some scientists proposed a provocative hypothesis that during the rapid inflationary period following the Big Bang, not every region of the universe expanded in the same way. Different patches, bubbles of space-time, may have inflated at different rates, creating pockets with radically distinct physical conditions. If this galaxy formed inside one of those slower inflating regions, it may have had more favorable conditions for rapid development. In this mosaic-like vision of the universe, each inflationary patch carries its own timeline, its own rules, some fostering accelerated galactic maturity, others unfolding in the slow, familiar rhythm we know. To push the investigation further, researchers began incorporating high-resolution gravitational wave simulations. Detecting such waves from this distance remains beyond current technological reach, but theoretical models offered a glimpse of what kinds of gravitational signatures such a galaxy might produce. The results were astonishing. The simulated wave patterns didn't match those expected from standard black hole or neutron star mergers. Instead, they pointed to something else entirely, perhaps the collapse of exotic matter, or even the remnants of a cosmic string, a relic structure from the universe's earliest moments. As Webb pressed deeper into its mission, a startling realization took shape. This strange galaxy was not a solitary outlier. It was part of a pattern. A second galaxy appeared, then a third, and soon half a dozen, all existing in similar early cosmic conditions. Each one bent the rules. Each one bore signatures that should have been impossible. Too heavy, too chemically rich, too structurally complex for their age. They were not clones, but they shared a defiant refusal to conform to the standard cosmic timeline. At some point, the argument for observational error collapsed. The sheer number and consistency of these anomalies eliminated coincidence as a viable explanation. What was emerging wasn't a fluke, it was a signal. A new cosmological model would be needed. One that didn't simply adjust the margins of accepted theory, but rewrote the foundations. One that could account not just for matter and energy, but for time and evolution on an entirely different scale. In parallel, the field of exoplanet research began to experience its own awakening. If galaxies were forming earlier than expected, then planets within them might have formed earlier too. This opened the door to a staggering possibility: that life complex, intelligent, perhaps even advanced, may have existed in these systems long before Earth itself solidified. Once far-fetched, the notion of long-dead civilizations or ancient biospheres suddenly became a topic of genuine scientific inquiry. Signals that had once been brushed off as instrument noise or statistical blips were reanalyzed in the context of Webb's findings. Astrobiology, once a field focused on where life might be, began to expand its scope to when life might have been. It now considered not only life in the present, but life that rose and vanished in the deep past, leaving behind no trace, but perhaps a whisper in electromagnetic static. Black holes, long viewed as destructive endpoints, began to take on a new role in this evolving narrative. A bold hypothesis emerged: that early black holes might have acted not just as galactic anchors, but as engines of creation. These primordial objects, if their properties went beyond what we currently understand, could have seeded stars, shaped galaxies, or even sparked localized expansions of space. They might have been the architects of the impossible galaxies themselves. In response to these revelations, the scientific community saw an explosion of collaboration. Quantum physicists, cosmologists, philosophers, and AI experts converged, united by the same urgent task: to interpret a universe that no longer behaved according to old expectations. Artificial intelligence tools were deployed at unprecedented scale to sift through the ever-growing flood of data. Machine learning algorithms began identifying subtle relationships between anomalies, patterns in brightness, structure, or spectrum that pointed toward a hidden order beneath the cosmic chaos. These patterns suggested a deeper framework, perhaps a fractal rhythm, a recursive blueprint that echoed across scales of time and space, as if the universe itself were composed of repeated structures woven into the very fabric of reality. What had once been the domain of pure theory, abstract math, and philosophical musing now had concrete data to build upon. The impossible galaxy was no longer just a curiosity. It became the keystone of what some researchers began to call cosmic archaeology, the study of a universe that may not have just one past, but many. Layers of time, overlapping narratives, and ancient structures that speak to something more fundamental than matter, a code, perhaps, that shapes all things, but reveals itself only when we dare to look deep enough. The study of this ancient galaxy was no longer about something far away. It became an excavation into the very fabric of reality. Not just space, not just time, but the deeper substrate that binds the two. The cosmos, it seemed, had hidden its greatest secrets not in the unreachable corners of distance, but in the complex choreography of its own unfolding. The discovery made by the James Webb Space Telescope didn't just shift the scientific consensus, it fractured it. It shattered the illusion that we had charted the essential nature of the universe. It reminded humanity of a humbling truth: the cosmos owes us no clarity. Our maps, as advanced as they may be, might still be scribbles drawn on the edge of something far more vast and unknowable. And yet, as researchers across the globe continue to peer deeper into the abyss of space, the legacy of that first impossible observation only grows. It has become more than just a chapter in scientific literature. It has become a turning point. In minds across disciplines, the universe is no longer seen as a completed puzzle, but as a living mystery. Space is not the final frontier. It is the beginning of something even more profound. No longer a void to be crossed, but a reflective structure, a mirror showing us the limits of what we understand. Through one improbable moment, the James Webb Space Telescope rekindled the true spirit of science, not certainty, but wonder. Not knowledge, but the pursuit of it. Not answers, but better questions. And that, perhaps, is its greatest gift. As Webb continued to explore the early universe, it became clear that the strange galaxy from the cosmic dawn was only the beginning. What followed was a sequence of discoveries that suggested the universe itself was not behaving as expected, not merely in distance or scale, but in the logic that governed it. One anomaly became many. These weren't isolated data points. They formed a constellation of contradictions, challenging the very scaffolding of modern cosmology. New observation targets selected from the same epoch began to yield results even more baffling. Some galaxies revealed not just surprising chemical complexity, but deeply unusual compositions. The expected ratios of hydrogen and helium were overshadowed by unexpected abundances of magnesium, silicon, and even rare elements like platinum. These heavy elements should have taken billions of years and multiple stellar life cycles to accumulate. And yet, here they were, fully present in galaxies that had only just emerged from the darkness after the Big Bang. This pointed to a mechanism no one had anticipated. Perhaps a hyper-efficient stellar generation process, or a more radical possibility: the direct synthesis of heavy elements through primordial particle interactions, bypassing stars entirely. If proven, it would dismantle one of the oldest assumptions in astrophysics, that stars are the sole forgers of the periodic table. Attention then turned to the spatial layout of these anomalous galaxies. The cosmos, long assumed to be evenly structured on large scales, now revealed subtle irregularities. These strange galaxies seemed to cluster in loose networks, suggesting the presence of some invisible influence guiding the matter, shaping it, organizing it. Some theorized the hand of a cosmic architect, a force or pattern embedded in the geometry of space itself. This brought new attention to the topology of the universe, the study of its global shape and connectedness. Could higher dimensional structures, imperceptible to human senses, be influencing how matter assembles in three-dimensional space? Some proposed that space-time itself may undergo local transitions, pockets of reality, behaving like phases in condensed matter, where the fundamental rules shift subtly, allowing for accelerated formation and organization. These so-called cosmic phase pockets could explain more than just rapid galaxy formation. They might also help make sense of strange gravitational phenomena and sudden bursts of complexity seen in the earliest cosmic structures. Further data brought another surprise. Some galaxies exhibited a startling rhythm, a synchronization of starburst activity, like waves of stellar birth sweeping across their arms in coordinated pulses. This coherence couldn't be explained by internal dynamics alone. It hinted at a shared influence, a connection. The idea of causal linkage across early galaxies, across regions too distant to interact, began to take shape. One theory proposed a lingering quantum field, possibly a relic from the universe's first microseconds. This field, oscillating across spacetime, could act as a kind of cosmic metronome, triggering synchronized reactions in galaxies otherwise disconnected. A shared beat in a cosmic symphony playing out over billions of light years. Meanwhile, some scientists turned their attention inward, not to the galaxies, but to the telescope itself. Was it possible that Webb, with its unmatched sensitivity and stability, was detecting more than light? Could it be picking up echoes, resonances from interactions outside the known electromagnetic spectrum? Signals from particles, or even faint imprints of exotic quantum fields. A few even dared to ask whether Webb was seeing traces of previous universes. The idea, drawn from the controversial theory of conformal cyclic cosmology, suggested that our universe is not a singular event, but part of an eternal cycle expanding, fading, and beginning anew. If so, then the impossible galaxies might be more than anomalies. They might be memories, echoes of worlds that lived and died before our cosmos was even born. With every observation, with every frame of deep space captured, the James Webb Space Telescope seemed to whisper the same message. The universe is older, stranger, and far more complex than we ever dared to imagine. And we've only just begun to listen. The mystery deepened with yet another strange detail. In several regions of space where no visible galaxies were detected, Webb's instruments recorded faint, low-level energy fluctuations. These weren't random bursts of static or background noise. They were structured too coherent to be dismissed, yet too irregular to be linked to known forms of matter or radiation. What exactly was creating these quiet echoes in the cosmic dark? The patterns bore an eerie resemblance to the theoretical profiles of decaying vacuum energy, what some physicists refer to as false vacuum states. In the context of inflation theory, these are thought to be remnants of the universe's early instability, traces left behind as it transitioned from one energy state to another. If these signatures are confirmed, it could mean something profound: that the universe has not yet fully stabilized, that we are still living in an unfolding cosmos, one whose physical laws are, even now, settling into form. Another frontier of discovery came through the study of light itself. Webb's polarimetry instruments, capable of analyzing the orientation of incoming light waves, uncovered something strange in the emissions from certain galaxies. The polarized light didn't match expected patterns, those shaped by cosmic dust or magnetic fields. Instead, the polarization seemed to twist, as if responding to an unseen hand. This led scientists to a startling possibility: interaction with chiral particles that behave differently depending on their orientation or handedness. In physics, chirality is a subtle but foundational feature. And if this twist in polarization truly stemmed from chiral interactions, it could offer an answer to one of the oldest questions in science. Why does matter exist in greater abundance than antimatter? If a chiral bias was present in the early universe, it may have shaped not only the structure of galaxies and stars, but the very foundation of chemistry itself. Astrobiologists took notice. Amino acids, sugars, and nucleotides, the basic building blocks of life, also exhibit chirality. They favor one orientation over another. If the universe itself contains a built-in preference, then life's architecture may not be accidental. It may be a product of cosmic symmetry, or rather, its deliberate breaking. This possibility reframed the question of life in the universe. Perhaps life isn't just an emergent property of complex systems. Perhaps it's encoded in the geometry of the cosmos from the very beginning. Webb's data, with its hints of handedness on a galactic scale, could be the first direct evidence of a universe predisposed toward life not by chance, but by design written into its earliest moments. While much of the ongoing analysis remained grounded in hard data, new lines of philosophical and theoretical thought began to emerge. One provocative idea suggested that what Webb had uncovered wasn't an anomaly in the distant past, but an artifact of our own place in the universe. Could it be that the laws of physics as we observe them are not truly universal? That they are shaped by the unique curvature and expansion of space from our vantage point? This concept, rooted in anthropic reasoning, proposed a radical shift. What if constants we take for granted, light speed, gravity, cosmic evolution, are not immutable truths, but localized expressions? If so, then the strange galaxies seen by Webb may not be breaking the rules. We might simply be misreading them. applying a local script to a far grander and more varied cosmic stage. In the end, the James Webb Space Telescope did more than deliver astonishing images or record distant light. It tore open a curtain between the known and the unknowable. It revealed a universe that is not static, not silent, and certainly not finished. A universe still in motion, not just through space, but through meaning. And maybe, just maybe, what Webb has truly discovered is not just the past, but the code beneath the cosmos. A living, dynamic reality that continues to surprise, challenge, and humble us. Not because it is unknowable, but because it demands we keep looking, keep questioning, and above all keep imagining.